Hi everybody. Um, Welcome to the live stream. Hope all is going well. As usual, presumably I'm here to talk about what's coming up on quiz 2. I'm happy to talk about, I guess, whatever in the course. If you have questions in the YouTube chat, wherever that is, relative to my face, I started a live Q&A in Piazza. I don't know if I can keep an eye on that or not. It's just one too many windows. But how are things going? What's up? Tell me, what do you want me to talk about? Because as with last time, I have no real solid agenda here. Um, so quiz 2 is covering the middle third of the course. I'm never quite sure how to say this. So not Haskell, not Go. So the stuff that is, about programming languages, language implementations, types of memory, concurrency, productivity, mixing languages, I guess. And the format, I guess similar to the first quiz. The TAs wish I had more multiple choice questions, I'm sure. I always find it hard to get good multiple choice questions in this course because there's a lot of things that are just a little bit more like write a function that when it comes to Haskell, or for this part of the course, a little bit more describe kind of questions. But I'm happy to look at the material here. So, um, um, so yeah, not this stuff, and not this stuff, right? So it's sort of this middle part of the course, and I guess corresponding to what assignment 2 is about. So yeah, there's no specific programming language in this part of the course. I guess I expect you to be able to read a programming language within reason. But yeah, I can't really ask you to write a function the same way as I could for like Haskell or Go. So yeah, the questions will be a little bit more based on these concepts from this part of the course. As always, like, memorizing a thing is probably not like, I'm not going to ask you. Well, yeah. So the question in the chat: would you suggest understanding / memorizing the terms? Understanding, yes. Memorizing, no. Right? I'm not. I'll tell you right now. I'm not going to ask you like what is the definition of kind of questions. I might ask you, like which ones of these, which term applies, or can you like what's the difference between these two things, or something like that, something more applied. If you is this I think this is the one I like. That'll do. Oh, there we go. I feel like I often end up pointing this out. I'm not one for educational theory, but I find students often who get into trouble, there's this, I don't know if Bloom's taxonomy is a great way to describe the universe, but whatever. Again, when people ask, like, should I remember the definition, I'm kind of imagining they're studying down at the bottom of this thing, like, what's the definition of, or what are all of the, or is this, which of these is a, I'm not asking questions down here. I'm almost certainly asking questions, on a short quiz, it's hard to create, but yeah, compare and contrast and distinguish and select and appraise. Sure. I'm much more interested in sort of that level of question. If that in any way helps guide your studying, that's a little bit more the kind of thing I'm worried about. So I don't know. Do we want to look at the what do you guys want me to do here? I can look at this part of the course, kind of do a quick look through the material if you want. I don't know. why don't I do that? If you have questions, put them in the chat. Feel free to sidetrack me as you need to. So, keep that. What the hell? I don't really have any sample questions to share. Yeah, I really don't. Except in that, I guess, exercise, what was it, 6 is, again, in this, it's the only real weekly exercise that supports this part of the course. I guess, to an extent, exercise 7 that did start the project, but again, it's these concepts that we have for this part of the course. Do you understand them? Can you apply them? Are they sort of functional knowledge for you? And I guess I'll start with the, like this, what do processors do? All this description of, you know, all of these CPU features that you bought, you know, again, they're in your processor, whether you think about them or not. I think this is more context for the rest of the part rather than kind of core material. Like, I don't know what possible question I could ask you based on anything we've done about this part of the course. Let's put it that way. Multiple cores are a thing, sure, but again, that's a fact that is just out there. Write good code. Hope your compiler helps. Okay. So I'm pretty much saying that this part of the course is not on the quiz. This is kind of where in my mind, the middle part of the course really kicks off, this language implementations. Yeah, okay. Right, so we had some concepts here that I think are probably not super new. Like, I think you've dealt with compilers and interpreters and stuff before, but you know, just in case you haven't, or in case you're, I don't know, the definition you had was maybe a little fuzzy or something. And I think this distinction, like compilers and interpreters are presented as if they're two completely unrelated things. In some ways, no. So languages like, well, Java, C#, again, anything that compiles to the JVM or the CLR or into LLVM bytecode, they all go through both processes, right? They're compiled from what you write in a text editor to that bytecode, and then that bytecode effectively is interpreted by something we call a virtual machine. Usually when you say interpreter, that's not what you're talking about, but and I think the other thing that is possibly new for people is this idea that Java, like what is done with Java and C# compiling, is no different than what is done to Python and JavaScript compiling. It's just a question of whether the step is explicit and you see the result on disk or something, or whether it's just part of starting up the process. Josh in the chat, yeah, I think so. What programming language do you know that fit these criteria? I think that would be a fair question. Like, I expect you to have some experience with some number. Like, obviously, I'm not going to ask you for like list 17 programming languages that have this, but I think for anything we've talked about, there's at least a couple languages on either side, where, yeah, like, I don't know, as I'm looking at this, like a language that's compiled to bytecode. Yeah, I know some of those. I just listed some. And I know some that aren't. C and C++ and Go are compiled to machine code, not to a bytecode. And right, in the compiler process, and again, and this applies to any compiler, whether it's compiling to bytecode or to machine code, all of those can optimize. And I didn't really, like, you know, I tend to hit godbolt.org on C examples where we're heading to machine code because the C compilers are really, really good. And they provide nice examples that I can kind of talk about. But there's no reason the Python compiler that's part of, when you run Python space file name or Ruby space file name, or when you load JavaScript into the web browser, there's no reason any of them couldn't do the same kinds of optimizations. They generally don't so much. And that's a good question, right? So sort of returning here, if I said like compile, like what's a language that's compiled to bytecode, it would have to be something like in the standard tools or in commonly available tools or something like that. Like, you can you can compile C to LLVM bytecode. You could, I guess, if you really wanted to, you can, like with Cython will compile Python to C and then C to machine code. So you can take Python all the way to machine instructions if you want. But any question like that would have to be like using kind of standard tools. I guess maybe, by the way, one of the other reasons that I might not expect something like the standard Python tools or something to do the same level of compiler optimization that a C compiler does is they do have a bit of a time budget, right? Like when I think of how fast is C code, I don't include the time that GCC spent taking my code and turning it into an object file. But when I run Python code, I don't see those as separate. So I kind of do have to, I think of that compile time as part of the runtime, just again, because it's part of the same process. So these optimizations are not free, right? There's a certain amount of computation to recognizing this pattern in the code and transforming it to something else. So that's, I mean, at least part of the reason I would kind of imagine most non-explicit compilers, maybe I'll call them, don't have the same level of optimization, but conceptually they could. And of course, there's a choice, right? Like we saw this in GHC. When I load code in GHCI, I don't get compiler optimization. By default, when I compile with GHC, I don't get compiler optimization, but I can turn it on. And the same story with GCC and Clang and everything else. So the thing that you can do at runtime is, again, I'm probably imagining here some kind of a probably compiled to bytecode system where I've got code that a programmer wrote, probably compiled it to bytecode, although not necessarily. And then I'm interpreting it, which is a virtual machine if it's bytecode. It's not going to be as fast as native code, but it's going to be in this sort of lower level representation. And a just-in-time compiler could be incorporated into that runtime environment. So I could, while I'm running, while the code is running, I could, I guess the environment, the tools could decide, you know what, this code is going to get compiled all the way down to machine code. That will be faster. Okay, so yeah, call in chat. Will we be asked to write optimized code? I don't think I can really ask you to write optimized code, just because I guess there'd be a question of in what language. I can't really ask you to write, I mean, I could ask you to write maybe very simple Haskell, but understanding that you haven't touched Haskell for a few weeks. And maybe the Go isn't quite fair game yet either. So if I was going to ask you to write code, it would have to be pseudocode or something. And I guess I could ask you to write pseudocode, but I do expect you to be able to read code within reason, right? If I say like, here's some C code, tell me things about it, or how will it run, or could a compiler do something like this to it, or some question like that. Any of those kinds of things where it's like more like reading code is a lot easier than writing code in a language where you're maybe not 100% familiar. So again, there's a couple of possible benefits here. Like almost certain, like there's a reason that C code is still typically ahead of time compiled, and that your operating system or whatever is ahead of time compiled, because okay, there's still a lot to be said for that, right? It happens ahead of time. It's right there in the name. So you don't have to worry about it while the program is running. There's no Like a just-in-time compiler has to do a little bit of like keeping stats on what's going on, and then it might have to pause a little bit and say, okay, well, give me a minute, I'm going to do some compiling, and then we can pick up again. And if you're controlling hardware, or maybe that's unacceptable. But on the other hand, there's no question in a just-in-time compiler of, exactly what SSE instructions are available. It's these ones, right? Like it's whatever ones are currently in the processor that you're running on. And if you compile code, if you just-in-time compile code that uses like the AVX2 instructions, but the next processor doesn't have those, that's fine, because it's only in memory and it's going to disappear when the program exits. Maybe you can do a little bit better like branch prediction or something, right? Like maybe it's possible where ahead of time you can't predict a branch, but at runtime you can just monitor the branch and see what happens. In a dynamically typed language, so this is where, and I guess I have this forward reference here, so this is maybe a good time to come back to it. In a ahead of time compiled language, if types are dynamic, well, what are you going to do? Types are dynamic. But at runtime, a just-in-time compiler can look at this and say, you always call, like there's 3 arguments to this function. The first one is always a string. The second one is always a float 64. The third one is always an int 64 or whatever. So we can compile a version of the function that takes those types, do type inference within the function, and then get static binding in a dynamically typed language if the just-in-time compiler is clever enough. So again, a bunch of options there. And as you've said, and as you've seen by now, yeah, there's different ways to implement languages. And it just depends kind of how much effort various people who are willing to implement languages have put into that language, right? Like people seem to like Python. There's a lot of tools that can work with it. And some are kind of integrated and some are completely separate tools or whatever. But yeah, you have a lot of options. I mean, a just-in-time compiled language call is it. I guess I'd have, if I was going to ask you that, I'd have to be careful, right? Like if you have a just-in-time compiler, it definitely is compiled. It's right there in the name. And even if you have a just-in-time compile, even if I say you have a language like PyPy is a just-in-time compiler, when I start up the thing, does it compile? I'm not really sure. A just-in-time compiler could take the strategy that as soon as it starts, like as soon as PyPy gets its hands on code, it takes all of the whatever came into it and compiles it to machine code right away. Or it could take the strategy of saying, I'm going to compile to whatever, some internal representation, some kind of bytecode, and I'll start running. And again, if this function gets called once and never again, fine, whatever. If this function gets called 1,000 times, I will then do the just-in-time compilation, and on the 1,001st time it gets called, it'll go faster. So it's hard to tell. Like you almost have to know exactly what tool and exactly the implementation details to say what is compiled in a just-in-time compiler. So it's a little bit of an unfair question to ask. Which I guess with that. So again, I had this example that oh geez, I added something. I added the code. I didn't actually update the results because it takes too long to run them. I forget what I added. Anyway, Swift or something like that. I did update these since I first talked about them in the lecture, but again, I think these running times tell a pretty big story that again, this is totally compiler bait code. This is designed to be very easy for a compiler to optimize. Like that's the problem I chose. But PyPy is running at the same speed as GCC-03, and that's a surprise, I think, to anybody who hasn't explicitly tried things like this. And Hip Hop VM is running basically PHP code, and that same kind of time range is a surprise. Within what is that, 5%? yeah, I mean, this, I like this benchmark because I spent a lot of time in it, frankly, but don't read too much into it. Oh, whoops, same one. All right. So other things we talked about, and again, these are all kind of related, so it's kind of nice to be able to do a bit of a review at this point. Um, the Anastasia, again, like if I ask you to write like it's very hard for me to ask you to write code because of course first question is in which language. So I think it would have to either be like write pseudocode, or I can expect you to read a sort of reasonable variety of languages, at least to figure out what's going on. But yeah, writing code is going to be very hard for me to ask. Okay, so static and dynamic typing. Yeah, like even in Haskell, like is Haskell statically or dynamically typed? Geez, I don't know. Like it certainly can be statically typed. Like if I rewrote this, if I wrote this code to, instead of this more generic version, be that, okay, this one clearly can be statically, is statically typed and can be statically bound by the compiler. There's no question. That is two integers being multiplied. This one, geez, I don't know. Like it is Haskell dynamic or static? It's hard to say. And even more, like I'm not sure, like what if I have this version and then let's see here. If I have code that does something like this, whatever that calls this function. Okay, even if this function, is polymorphic and can take arguments in different types, what are you doing? Am I back? I guess I'm back. I don't know what happened there. Sorry about that. I don't know what I said last before my stream dropped there. Okay, sorry. Hey, it's all Tellus's fault. Anyway, yeah, so maybe the compiler could take the strategy here of, okay, I could compile this function for any numeric type, but I'm going to compile it just for integers because that's how you used it. And I'm not sure, to be honest. I don't know what Haskell's going to do. So again, like this distinction between static typing and static binding, dynamic typing, dynamic binding is pretty thin. Static typing is about what the compiler knows about different types. Binding is about whether the operations can be linked to an implementation, and those are very, very closely related, obviously. And let's put it this way: the question on there's no question on the quiz that is like describe the difference between static typing and static binding. If that makes you feel any better. But again, does a compiler know about the types in the code or not? And we've seen static binding is a huge benefit in speed. If I know that is integer addition or floating point addition, then the code doesn't have to look up at runtime, what do I do with these two numbers? And then how do I combine that result with a third number? That's a big difference in speed. And it's the difference that is in the Python implementations, certainly this one. So Python with static type hints in the code allows the creation of a statically bound implementation, whereas Python without those type hints in the code is, so what was it, about 10 versus about 370, so 37 times different. Yeah, again, not all code is going to be that distinct in the runtime, but it's a big difference there. And this is why, like, when I look at times like this for PyPy, even though I gave it dynamically typed code, it must be binding. It must be static binding somehow. Like when it does the just-in-time compilation step, it must be implementing or compiling, I guess, this function into something that is statically bound. I don't see any other way that the time can be the same as optimized C compiler output. Again, without proof, but I don't see any other way to explain that evidence. Again, there's a few examples here that a little bit tease out that distinction between static typing and binding. Somewhere here. Oh, I'm getting ahead of myself. Anyway, so this method call has to be has to be dynamic. Like there's some dynamic lookup on that in Java because I don't know what subclass of this I'm getting until runtime. Sorry, was there anything else that I missed back here? I don't think so. I think some examples of that static binding stuff I talked about. So again, like Python can be statically bound, at least, just in a just-in-time compiler if it has some guard like this on the types of the function calls. A static looking language can have dynamic binding if it sort of allows some feature like that. Like in C++, the answer is no, you do not statically, we statically bind everything. You do not get to do dynamic lookups. You can get there, but you sort of have to implement almost around the language somehow. Type inference being one of the ways that sort of, like, I guess maybe like my complaint for explicit static typing is I have to declare everything. I don't want to declare the type of every single thing in my program. It's a waste of keystrokes. Type inference is a way to get me around that. And we've seen this in, well, in modern C++, type inference on variables where there's an initializer. So whatever type that expression returns, that must be the type of this variable. What else could it possibly be? So I don't have to say it explicitly. Or in Java, or we've seen it by now in Go, at least in lecture time. In, where else does it come up? Like it comes up in Rust actually more than some other languages. Like this simplest kind of type inference, everybody wants this. It seems very clear that everybody wants to be able to do this because every language off the top of my head includes it now, other than, I guess, plain C and not C++. But there is this, like we saw Haskell do a lot more type inference than that, and it turns out Rust can do a bunch more type inference than that as well. We see a little bit in Go when we start, let's see, when we talk about, I guess, defined types in Go. So in Go, you can say, so we've done like this, right? Like create a new type that is a struct. It turns out you can also say that. You can define a new type that is an alias to a built-in type. And then you can end up in situations where there will be a little bit of type inference of, how do I spell this? It's a very, very minor kind of type inference, but like this is inferred to be of this type, not an integer, not a normal float 64. So it's the only way to make this statement work is if this is one of these, not one of these, and that type inference will get done. Again, very, very minimal kind of type inference, but it happens in Go. Along with this type inference, right? That this variable must be of the type of the thing it's being initialized to. I think a lot of this, the duck typing is one of those, it's a funny term that I almost feel like doesn't need to be a term. Like, okay, well, if you just take, it's almost just if you write code and it doesn't throw an exception, that was okay. Like, does that really need a term to describe it. Like, okay, I can write this code, and as long as I don't do anything to these types that's illegal, like if this first argument is an integer, this is going to fail because you can't iterate an integer. Or if this is a list and I get strings out of it, but the second argument is an integer, I can't compare strings and integers, so that's going to fail. But, well, as long as I kind of don't do anything that's going to fail, it will work. Duck typing. I don't know if I need a term for that, but there you go. Again, type checking, the strong and weak typing that as a descriptivist, I don't know what these words mean. This seems to be what people think these words mean. If the compiler checks a lot of things, then it's strongly typed. And if the compiler keeps you safe, it's strongly typed. If it doesn't or it can't, it's weakly typed, I guess. And these, I just hate I hate type coercion in a language so much. I know I said it when I gave the lecture, and I still hate it. Mutable and immutable, again, it's a feature that the language can give us to sort of explicitly make this distinction. Like the concept of like, I have a thing and it's mutable, I have a thing and it's immutable. You can do that in any language. I think the question for us in this course is, will the language help me? And I guess we saw a little bit like Python will refuse to put certain things into a dictionary. So they kind of check mutability in a very specific way. And then languages like Rust, where's my Rust example? Rust is very explicit about it. And again, one of a very small number of languages. Like we're seeing, did I just do this in a lecture? Yeah. The lecture today on Go, we saw Go is like teasing us with a feature like this. It's almost like you can have a mutable or like a method on a struct that is mutable or immutable, or that like gets a mutable or immutable copy. And it's almost true. It's almost what you get with the receiver argument in Go, but not quite. Rust has this much more explicit and real. You can, like inside the function, we can change this thing. Inside the function, we cannot change this thing. And it's very clear because I see what kind of reference I get. So memorize, I guess this is another callback to today's lecture, right? Like it turns out Go, I mean, I can think of having a stack and a heap in Go. Go just has memory. You have a variable. I'll put it in memory. That's all Go really promises. This picture, whatever. Stacks and heaps, it's all just memory. Stuff goes in memory. You as a programmer should just move on and I guess know that garbage collection happens. But most languages have some distinction here of the things that are very obvious when they disappear, and it's when the function returns, and these things that are much less obvious when we're done with them. So the question is, who takes care of this? And the answer in C and C++ is the programmer. It's your job to free or delete. Del is Python. Or will the language take care of it? And I think, here's my challenge to you. I know how much free time you have, lots. Go back to some C++ code you wrote, like, early days, like when you first learned about the new keyword in C++. How often did you delete? Like how reliably did you delete the thing that you newed? Always? I bet not always. It's just hard to do this. And it's annoying. So the smart pointers in C++, what is it, 11, will help at least. As long as you use them, of course, and you can use them at sort of maybe the module level. Like I have a class. My class takes an argument in its constructor. I'm going to build a thing and use a smart pointer. And then inside, I can use the dumb pointer inside, or I guess it takes the argument as a smart pointer. Inside, I can use dumb pointers. Inside my class, this thing is going to live as long as the class lives, and I understand that. And then the smart pointer will be destroyed when the class, the object itself is gone, and that will take care of the memory leak. And Rust doing this with explicit ownership is interesting. So I guess we kind of have three things here, right? There's programmer does it, manual memory management. Runtime environment does it, garbage collection. So the runtime environment looks around and says, okay, you're done with this. I'm going to free it up. Or the thing that, as far as I know, is only happening in Rust, although is also implicit in the smart pointers in C++, is the compiler figures it out. The compiler knows you're done with this at this moment in the code. So once you exit that function, we're done with this object, this bit of memory. Okay. First class functions, I think we know what this is. Like, I think once you come across this in a language, I think it's reasonably obvious, right? That you can pass a function as an argument. You can return a function as a result from another function, like this one is doing. So I think we're okay there. Closures are a little more interesting. And I'm curious, I guess maybe if I was a better instructor, I would do one like a poll or something. Yeah, I don't know how to set up a poll. Certainly not in real time. How many of you knew what a closure was? Like, I'm curious, like how many people realize now that they have used closures in the past without ever knowing what they were? Like, I think people write this code sometimes, like in languages like JavaScript that kind of promote these like anonymous functions that get passed around. You know, this function has end closed. And if I was using this as a callback for some jQuery something, yeah, I'm using closure probably without ever realizing it. And again, the callback style, again, I think once you realize that first class functions are a thing, we can pass a function as an argument, a callback becomes an obvious thing that you might be able to do. Okay, so we have at least one. Yeah, but okay, one person has voted yeah. One of you, did you not know what a closure was, but use it by accident just because you wrote that code? That's the real question. And I mean, of course, you don't have to mentally review every line of code you've ever written, but I'm curious. Yeah, so in code like this, right, it's very easy to write an anonymous function here that does something like this. That includes a closure, right? Like I have some variable that's defined up at this level and I use it in here. Well, that's closed, right? So this function is going to run later, probably after this function has exited and the local variables are long gone. But if I use a local variable in here, it works because closures. Yeah, see, if you've written JavaScript, I bet you've used a closure. Again, anytime, like if I use a local to this function variable in the anonymous function inside it, it's closed. JavaScript programmers use closures all over the place. And again, usually without noticing, because it just kind of looks like it should work. Okay, coroutines. I actually have, let's see, I just recorded it. So I guess next week in Go, this is not very helpful for the quiz, but I'm using coroutines as coroutines as coroutines in Go in a couple of lectures, which they kind of are, right? Like these functions that kind of take turns. Okay, so the Python example, it's in one thread and then it's just sort of, okay, I'm going to pause now while you take my result and I'm going to ask you for another result, so wake up again. It's in some specific problems, a really nice style to be able to use. So in Go, we can use Go routines to do exactly this thing, and it's concurrent. Oh, it's parallel also. It's in separate threads. And undefined behavior because C++ hates you. Any questions in there? Okay. Let's see that and that. I guess I better hut too if I'm going to get done this by 20 after. If you have questions, but again, do feel free to put questions in the chat. Like I know I'm talking because it's what I do when I sit here in front of this camera, but if you have questions, feel free. So So concurrency and parallelism, again, are obviously related, but again, the Python coroutine example there is concurrent but not parallel. The analogous code in Go would be parallel because you have separate threads. Again, for this course, I want the language to help. So that's going to mean things like, well, if I write pure functions or I have immutable data structures, that's going to help. And if the language guarantees it for me, like if there's something I can do in the language that says this, you know, when I pass this argument to this function, it is immutable, well, then I can pass it to different functions running in different threads and not worry. If the language doesn't assure me of that, then I have to worry. I have to make sure that that function doesn't modify the thing. Or again, if I have a pure function that doesn't modify the thing and doesn't do anything other than return its result, I know exactly how that code interacts with all the other data in my program, which is not at all. Again, another question of like the language implementation. When I create a thread, is it a kernel thread or a user thread? And somebody asked, like, so p-threads, the concept of p-threads applies to either one of these. P-thread is just, there is some concept of a thread. I can start one up by calling this C function. So saying p-thread doesn't necessarily imply either one of these, or a hybrid, a small number of kernel threads with a large number of user threads embedded in them, also, which is what Go does. So I think, Nicole, how to prep for the quiz. Again, I'm going to be asking, I kept that open, you know, I'm going to be asking as much as I can, at least questions up towards the top here. Again, you can't really build too much for this quiz, but certainly apply, analyze, evaluate. So don't worry so much about remembering the definition or the list or whatever. What's this word about, you know, what am I doing here? Like, why would I care? If I'm a programmer, why would I care that my language / library gives me kernel threads versus user threads? What's that going to imply for the code I write and what I can get done? And, you know, the most obvious example here is, well, I can have, I don't know, a few dozen or a few hundred, because, you know, starting up a user thread is cheaper. I can do it for a smaller job than I would for a kernel thread. That's not a huge distinction, but maybe I need to know as a programmer. At least maybe keep it in mind. So, right. I didn't say much about this at the time, but we are now seeing channels in Go as a way for two threads to talk to each other, effectively a thread-safe queue. And we've started to see things in languages where the language is helping us. Language is making it easier for us to get the thing done with parallelism and concurrency involved. Those of you who did Erlang for assignment 2, well, I at least have another example of that. I forget what the other options were, but yeah, some of your assignment 2 options, maybe you have another example in your head of various tools that can do things in parallel. And I like that. And even though in some ways this is not relevant to the course, like, oh, look, here's a thing I can do. Look, here's a thing I can do. In Scala or Python, like, I just want to point this out. Like parallelism doesn't have to be hard. In general, it does. You know, in general, if you're writing an operating system, yeah, you got some mutexes and semaphores to worry about. But if you're just trying to get some computation done, maybe not. Okay, I think the last topic in here, well, sort of, is this. And again, I don't know what kinds of, there's just so little concrete fact in this part. I don't know what I'm imagining I can ask you here. Which is annoying because this is the part I care about the most. Usually I don't care about runtime. Like, think about the code you've written. How much of it was CPU bound? You know, I guess unless an instructor was really trying hard to give you a problem that had a lot of CPU to test your implementation or whatever. Usually not. So again, I think all of these, I think they all point to the same conclusion, which is people tend to be more productive in higher level dynamic languages than in lower level static languages. But maybe that's just my own bias. Like I certainly am more productive in Python or Ruby or JavaScript than I am in C or C++ or Java, but that also could just be my own programming experience. I've written more Python and Ruby and JavaScript than I have those other languages in recent memory. Again, there's nothing I don't know what I can test you on. Libraries are available. That's cool when they are. Again, I've also high level versus low level language. It's another one that I find really hard to define. There's languages that are obviously higher level. SQL is obviously a very high level description of the thing you're trying to do. C is obviously a more low level description of what you're trying to do. And I think part of the reason I wanted to talk about this, what do processors do topic, is people, I think C programmers think of C as the ultimate low level language. Well, not really. It's not like C maps onto your processor perfectly. It did in the 70s, but now there's a big difference between what your CPU is doing and what you're expressing in C. Again, I think, imperative and declarative, I think we have probably seen this well by now, right? Do you give a series of steps that modify memory, or do you say, here's a computation I need done, or here's a result I need done, please compute it for me, in a declarative style? And we have seen functional programming as one declarative thing we can do. There's others, things like SQL or a Prolog that I'll spend a few minutes talking about in a week or two. And I think that's probably that. The mixing languages topic here, again, conceptually, it's part of this middle third of the course, but in practice, it's supporting the project. Like, you'll have plenty of chance on the project to mix some languages together and see how that goes. I don't know what I could possibly ask you in the quiz that heads down this path. That being said, I know the project is more work. Like, if you had the choice of final exam or project in this course, the final exam choice is probably less hours of your life, but I think the final project is cooler. Like writing some code that mixes multiple programming languages together. Most people don't do that and don't have a chance to do it, or even just realize that it's not so hard to do that. So we're coming towards 20 after. If there's any last questions, whichever direction the chat is, feel free to, well, I guess say them soon, I guess. Speak now or forever hold your peace. Overall, as the course goes by here, again, we're doing quiz 2. I'm actually done recording lectures. I recorded the last lectures yesterday. So the schedule that's on the website now is the final schedule of lectures that we'll have. Project is greater than exam on what metric? Is it your own personal enjoyment, time? Your estimation of how you will do relative to the rest of the class? Any of these are acceptable measures of a course, but anyway. So yeah, I'll have lectures in week 12. The Tuesday of week 12, I'll have an hour, like a solid hour of lecture. And then I'll do another live stream before quiz 3. So there's like 4-ish hours of lecture left after this, and another hour of live stream and a quiz around assignment 3 and quiz 3 around Go, and a final project. Don't leave the damn final project off. Like, I introduced exercise 7 this semester to force you to start the final project, because last semester your classmates really left it off and didn't, then we're all annoyed at me because of the workload in the last few weeks. So no, I'm not gonna release those videos early. I think I'm gonna keep the steady tick-tock of 3 hours of lecture a week. Yeah, I'm not gonna release them early. I'm gonna maintain the fiction that we are having 50-minute lectures where we all get in a room together at certain times. I like the fiction. So anything else as we are how long have I been streaming? Where is that? 51 minutes. So I guess class is over and you all should be shuffling around nervously with your books trying to get the hell out of here because it's hot and you have to get to your next class. I don't know if that's what's really happening or not, but what will your projects be marked on? There's, I think down at the bottom of the project description, there's a list of things that we may look at. That sounds like something I remember writing. Yeah, there's a list of 5 things down there at the bottom of the project description. Final tips for the quiz. I think, know the material. Don't overthink. Like I see a lot of people, especially on the really fast quiz, it's like they know the answer, they write the answer, they panic, they change the answer, and they get it wrong. Don't panic. I know 30 minutes is quick. Hopefully you're not too time limited on it. It's really hard for me to strike that balance. Hopefully I managed to do it okay. I think that's all I got, and I think I probably should stop there because, well, our time is up. So yeah, good luck in the quiz on Thursday. And yeah, I will see you, as usual, like I'll be in the live stream during premiere during the lectures. If you have questions in there and whatever office hours and Piazza and stuff between now and then. Don't worry about the curve. I mean, maybe, but let's not talk about that here. If you want to ask in Piazza or something, I can give a better answer. But yeah, I'm going to stop there and tell you all good luck and see you in a live stream in a couple of weeks for quiz 3, I guess. Bye, everybody.